What is method of image? Method of image is a very powerful tool that is taught at BSc Physics level in electrostatics. Using this tool, you can find force between large parallel conducting sheet and a point charge placed in front of it. And there are many more applications. My name is Brajesh Chaudhary, and this video I'll teach you method of image and its one classical application. The license to apply method of image comes from a very important theorem in electrostatics that is called the uniqueness theorem. But uniqueness theorem employs terms like Laplace equation, Nabla operator. Often a student who is in class 11th or 12th has no idea about these terms. So I want to present uniqueness theorem in a very lucid and simple term. The motto of this video to make a class 11th and 12th student able to understand what is a method of image and start applying that without knowing exactly what the uniqueness theorem is. But still I'll state uniqueness theorem, but before that let's understand one situation. Suppose I have a point charge Q and I want its electric field and potential at a point P, X, Y, Z. The origin of the coordinate system is at the point charge itself, and that is a very straightforward method to find electric field and potential, and I can directly write potential is equal to kq divided by the distance from the charge to that point. And similarly, electric field is kq by r square, that is the magnitude, and direction is in the radially away direction. That is a normal way. Here k is a 1 over 4 pi epsilon naught. But let me change the situation a little bit. Again the same charge there, same point where I wanted to find electric field and electric potential. But now what I have done, I have put a little conductor in front of that point charge. So what will happen? Will the electric field and potential be still the same as it was before, or it will alter? Conductor has a lot of free electron that can very nimbly move at the surface. So when a positive charge is placed in front of it, the negative charge will come towards that positive charge, and the points which are farther from that positive charge, there will be deficit of the free electrons, so there will be positive charge. And now how these surface charges, though conductor is still neutral, but still that is divided into plus and minus charges. Now how these plus and minus charges distribute themselves, that will be decided by in such a way that a net electric field because of these charges and the charge that plus q was placed there. So net electric field due to all charges in space becomes 0 inside the conductor. So that will not be a very good distribution of the shape, is not very good. So I have no idea how charges are distributing at the surface of the conductor. It could be simple, it could be very complicated. So now to find electric field and potential at point P is a very tough job. But fortunately there is a way, and that way is the uniqueness theorem. So what does uniqueness theorem state? Uniqueness theorem states due to some charge distribution, potential in a charge free region is uniquely determined if value of V, value of potential, is a specified function on all boundaries of the region. Suppose I have some charge distribution and I want to find potential at a point P in a charge free space. For that thing, and the problem to find that this charge distribution is a very complicated thing, and I cannot find potential by integration of k dq by r because the distribution is very complicated. So that is a problem. So what I want to do, I have a license from the uniqueness theorem. First of all, I need to know the potential at all boundary points. The potential at the boundary points I know, these are the boundary points. The blue ones points are the boundary points where I know exactly what is the potential for this charge distribution. And now I will think of an alternative charge distribution. If the alternative charge distribution gives me the same boundary condition, what does it mean? The same potential distribution at the same boundary points, then according to uniqueness theorem at the point P, I will have a same potential because of this alternative charge distribution as it was because of the original charge distribution. Because the uniqueness theorem says that for the given boundary condition, the potential is unique. Charge distribution can have different. Two different charge distribution can give the same boundary condition for the potential. If the boundary condition for the potential is same, so different charge distribution will give the same potential at a point. So if I have a complicated charge distribution and I'm not able to find potential or field or force, so what I need to see, I need to look alternative charge distribution that gives the same boundary condition for the potential. Then I will find the potential because of this alternative charge distribution, because that is the guarantee, that is the license I am getting from the uniqueness theorem. And now its application is the classical image problem. What is that? See, in the classical image problem, there is a large infinite conducting sheet and it is grounded. Even if it is not grounded, one thing is that conductor has a potential same at all points. Because it is an infinite sheet, the points at infinity has a potential 0, so all the points are at potential 0. And if it is given that it is grounded, so no problem. So it is grounded. And in front of it, I have chosen a coordinate system. XY plane is in the sheet itself and the Z direction is perpendicular to plane. And there is a point charge Q placed at a point 0, 0, D. This is in communication with the ground, so charge cannot be conserved. Charge can come from the ground and go from here. But because of that positive charge, some charge distribution will be there, some induced charge will be here. And because of that, force between this point charge and the sheet will be there. What we want to find? We want to find two things. We want to find potential at a general point. The sheet is Z is equal to 0 plane, XY plane. We want to find potential at a general point, which is X, Y, Z. And another thing I want force between plate and charge. So for that thing, the charge will distribute in a very complicated way, so there is no way I can find potential and the force by the normal Coulomb's method. So I will have to look an alternative charge distribution that gives me the same boundary condition as this. So what is the boundary condition for this distribution? Boundary condition is that at Z is equal to 0, that is where the sheet itself potential is 0. So that is the one condition. And if we go large distance away from this point charge Q, so because of this point charge Q, if you go very large away, so then again the potential should be 0. So very large away mean our origin you can see. So at a very large distance, the distance will be square root of x square plus y square plus z square, and that should be quite more compared to where the charge is. So v will again tend to 0 for x square plus y square plus z square is very large compared to d square. So in other words, I want to say that the potential is tending to 0 at a points very far away from this point charge Q. So now I need to look an alternative situation which gives me the same boundary condition for the potential as this charge distribution. This charge distribution means this distribution for the sheet and a point charge gives me. So that alternative situation is this. So in the alternative situation, if I put 2 point charges, 1 point charge plus Q at 0, 0, D, mean the 1 point charge is the same where there was a charge in the previous situation, like this. This charge is at the same position, and now there is no sheet, there is no conducting sheet, but I have put another point charge at minus Q at 0, 0, minus T. Why this method is called method of image, you can see now. If you think that the xy plane as a plane mirror, so this minus Q charge is the mirror image of the plus Q charge, and that's why this is called the method of image. Now see, in the previous case, the potential at all points on the xy plane means z is equal to 0 plane was 0. So you see that if I take any point on this xy plane like this P, So any point on this xy plane is equidistant from the plus q charge and minus q charge, any point. So if these 2 points are equidistant, so net potential at this point will be 0 because distance is the same. There is a plus charge, plus q charge, there is a minus q charge. So this distribution is also giving me the potential 0 at z is equal to 0. And obviously this distribution is a kind of a dipole whose length is 2d. And if we look for a far away distance, this dipole will appear to be very short dipole. And at a very far away point from a dipole, the magnitude of electric field is kp by r cube square root of 3 cos square theta plus 1. So there is upper limit, and as r tend to infinity, that will be 0. So again, at a very far away point, the potential will tend to 0. So what you can see that this alternative charge distribution is giving me the same boundary condition as the original charge distribution. So now we can easily find what we intended to find. So we got the same boundary condition. So now what we wanted to find, we want to find the potential at point P x comma y comma z at z greater than 0. So here is that point. Suppose this point P is at a distance r1 from plus q and r2 from minus q. And using coordinate geometry, you can find r1 will be square root of x square plus y square plus z minus d whole square, and r2 will be x square plus y square plus z plus d square and whole square root. So then using the superposition principle, you can find potential at P, that will be kq by r1 plus k minus q by r2, and simplify thing and put the value of r1 and r2, we can find no potential at any point on a space. And the same way we can find the force between the plates. So I will not look the plate and the charge. Sorry, I've written plate and conductor. I should have written conductor and point charge. So in place of the point charge and the plate or conductor, I will look the 2 point charges, plus q and minus q. They are attracting each other. So the magnitude of force will be k into charges, product of charges, and distance square. So the magnitude of force will be kq square by 2d whole square. That is the amount of force they are exerting on each